It's a great pleasure to open this event, to open this very nice, to be in this very nice place. And thanks Alessandro, thanks Nadia for inviting me and giving me this, the best slot or the worst slot, I don't know. We'll see. Right, so I'm going to talk about graph neural networks and their expressivity. It was a little bit difficult for me to understand what is the audience. So some people maybe already know a lot about it, some people maybe know nothing, but we'll see. I hope I will tell something useful for everyone. Another thing is that, okay, I don't know how it will go. It may go very slowly, it may go very quickly. So maybe, we'll see how it goes. Okay, so maybe I will not have time to present everything. But anyway, so nice to see you all and nice to see lots of faces I know and lots of faces I haven't seen for years. That's, thank you for coming. Anyway, so in recent years I started to graph neural networks and I'm really excited about this topic and I'm really excited about the connections of graph neural networks and my usual stuff, logic and other formal computer science. And I hope after this talk you will have this feeling as well. Generally, yeah, okay, I'm, let's say, forgetting about my PhD and stuff, I'm generally a logic person. And graph is a standard thing for logic, right? So we love graphs. But in recent years, machine learning people started to love graphs as well. They basically understood that usual neural networks are not good enough for many things, for abundant problems where objects are graphs, and they basically invented graph neural networks. Well, okay, they were invented kind of ages ago now in 2008, and there is a debate who did it, but actually they become kind of popular only less than 10 years ago. Until then, no one cared. But nowadays, they're really popular in machine learning. So graph neural networks, working on graphs is, okay, maybe now it's in a little kind of way down, but in recent years, you may see like lots of hundreds of papers popping up every year about graphs. And they are applied to many, many problems where actually sometimes they should be applied, sometimes they should not be applied. But I guess most of you know some problems on graphs and some problems where machine learning on graphs is applied. Yeah, so I borrowed this picture somewhere, doesn't matter, but yeah, you know the examples. But basically, the goal of this talk is, at least for an average person in the audience, is to understand what are these GNNs, what are graph neural networks, and we will see that it's actually a family of formalisms, not just one formalism. Then we want to understand what these GNNs have in common with classic formalisms. Say, isomorphism tests, this maybe many of you know. Well, bisimulations, connections of GNNs with bisimulations, this is maybe very few of you know, but I'm happy to present it. And like logic, as I guess many of people here have ideas about logic. And surprisingly, okay, graph neural networks, they're neural networks. It's good to understand it, right? So they have all these matrices, vectors, and learning parameters, all this stuff. But somehow we can link them to logic, and we will see that they have lots in common with this symbolic. Oh, so is it a problem in hearing me? Like this? Okay, as I say, I'm not very used to this type of mics. Anyway, so, and then finally we will see how these results, these connections to logic, and okay, not only logic, classical formalisms, can help us to learn something about these graph neural networks. So basically, it will be useful to understand what we can do with graph neural networks and what we can't do with these graph neural networks. So generally, we will see that there is no universal approximation theorem for graph neural networks, contrary to like usual neural networks. So not every function on graphs can be in any sense be expressed, approximated, whatever, with graph neural networks. So they have limitations. We will discuss it. Generally, as okay, I keep saying about logic and all these things, generally I assume that the person who listens for me here know what is first order logic and some ideas at least, and what is the basics of machine learning and neural networks. Yeah, I see some people here who may have zero idea about this. Sorry about that. But I hope you get at least some impression about what's going on in this type of science. Okay, yeah, if you know something about graph neural networks, it's also good. But if you know too much, maybe it's getting a bit boring for you, this talk. But anyway, let's start with graphs and graph learning. So what actually we are talking about. And generally, well, we keep saying graphs, graphs, but we need to fix what is the graph. And apparently, different people mean different things on the graph. So of course, they can have common grounds, and this is what I try to do here. Basically, it's a standard, undirected, not labeled on edges graph, where each node is actually has a labeling, which is a vector of numbers. This is my model for today, okay? This is maybe for logic people is a bit unusual, but for graph learning, this is what we usually assume. These assumptions about like undirected and not labeled edges is just for simplicity. You can generalize all the stuff we'll talk about to the settings where we do have directed edges, we have like labeled edges and so on. While simple, no self-loops, no repeated edges, this is also very minor. So, do you see this thing? How to get rid of this? Oh, Yeah, okay. Fine. That's why I don't like other computers to present with. Anyway. So, what is graph learning? Generally, I concentrate on so-called node embeddings. This means, yeah, okay, there is this definition, but basically, what we want to learn, we want to learn a function which assigns some answer yes or no, or maybe a number, to each node in each graph of the type I presented. Okay? So we have graphs, and then we have all pairs, the graph and the node in this graph, and we want to learn so-called node embedding, a function that is of the form like, okay, each pair of graph node to some output space. This output space may be, I don't know, yes, no, for classification, or a number for regression, or in principle, whatever. And the simple example of this node embedding would be, we have like some networks, and we want some network of paper citations, so which paper cites which paper. Well, in this case, it's probably a cyclic graph, but it doesn't matter. And we want to say, to predict a number, 0, 1, like relevance for every paper. And of course, these papers, they have some vectors, some lambda, which represents some information about this paper. As I say, we concentrate on node embeddings, because we say yes, no, or a number for each node in the graph, in each graph, but we can generalize this to graph embedding setting, when we say yes, no, or something for each graph in general. But I generally concentrate on node embeddings in this talk. Okay? Good. People are a bit scary, or I don't know. I'm scary. Oh, yeah, of course. I'm Russian. All Russians are scary. Especially now. Well, and I understand why. Anyway, so first question would be, okay, we have these graph embeddings. Why can't we use usual neural networks for this, right? Deep learning, right? Well, there are a couple of problems with this. So the first problem is that for fully connected neural networks, we may need a lot of layers, a lot of weights to learn. So if we have like a graph, reasonably sized graph, I don't know, for simplicity, like, some grid graph with some reasonable dimension, maybe a picture. And then if we just have like one neuron for each pixel, for each node in this grid graph, then if we want to add all the connections for one layer, we will have like crazy amount of weights to learn, right? So it's already impossible. But there is a more kind of fundamental problem. So this is scalability, yeah, that's fine. But the more fundamental problem is that if the size of the input is fixed, then deep neural networks work. But for graphs, we want our function to work for graphs of any size. Right? So we want to learn on small graphs and apply the same thing for arbitrary large graph. And this is actually like a problem for deep neural networks because they have fixed sized input. If you train for vectors of size 25, okay, it works for vectors of size 25. There are, of course, like neural networks models which work for different sizes, like RNNs, like Alessandro knows very well, or CNNs, convolutional neural networks. They work for like images of arbitrary size. But, well, okay, of course you can do something with like some complex embedding of these graphs to some fixed size vectors. But this is what you want to avoid, right? You want to work naturally with graphs. And this is basically what GNNs do. And, well, if you don't know graph neural networks, but you know, like, say, convolutional neural networks, then basically GNNs is a generalization of CNNs to graphs. If you look at CNN as a grid, as a graph where the nodes are pixels and our neighbors are like neighbor above, neighbor left, neighbor on the right, then a GNN is just generalizes this setting to arbitrary graphs. And let's have a little example. So if we have some graph, a molecule in this case, then yeah, okay, it has typed edges, but it doesn't matter. And then we want to use the structure of this data in our learning. So how can we do it? So we basically have several layers with the same graph, but we propagate our information. We propagate information, say, for each node kind of individually. So for this first node, we take the information from the node itself and the information from its neighbors. We have just one neighbor. And for the next layer, we have somehow some complex functions which we learn from taking the information here and from the neighbors. For the next node, maybe this one, we take its own information and from the neighbors, we have two neighbors in this case, and somehow aggregate this information to the node. And we go like in parallel for all nodes, do some like new node embeddings, new vectors for these things, and continue to like next layer, next layer, and next layer. Okay? Anyone not following me? Okay, everyone who wants follows. So basically, okay, if we want to formalize it, a GNN is basically a bunch of functions. It has several layers, fixed number of layers, L, and for each layer, we have an aggregation function and a combination function. And then finally, we have an output function at the end. So the aggregation function, what it is, it basically takes the multi-set of vectors from the neighbors and aggregate them to one single vector. And then having this one, having the resulting vector, the aggregation, it combines this aggregation thing with the value on the previous layer for the node itself. Right? So for each node, we collect the information from the neighbors, combine it with its own information which we had on the previous node, and get the new value for this node. All right? And at the end, we do some output. Basically, for each node, we produce the out, maybe yes, no, using threshold or something like this. Okay, so basically, this is how it works. It inputs a graph with some nodes, some edges, and some embedding, some vectors for each node of some dimension. And a run is just initializing for the first layer with this lambda, and then iteratively compute the embedding used the aggregation function first for the neighbors, and then the combination function with the value of the node itself. We do it for several fixed number of layers, and then output a value. This is how we run the GNN. So basically, these GNNs realize node embeddings, right? So we really say something for each node in each graph. Of course, we can generalize this setting for graph level when we say something, yes, no, or a number for each graph itself. So you may ask me, okay, then where is anything neural here? So that setting I presented you is very kind of general. Of course, in real life, we do have neural stuff. We do have matrices and vectors and some learnable parameters and all these things. And a very simple, basic, say, sum plus GNN example with sigmoid looks like this. So basically, our aggregation is usually like sum or maybe like something else, but in this case, it is sum. So we sum the vectors of the neighbors and then combine it. So everything else is basically the combination here. We combine it using some, like the value of the node itself, then some matrices. This is like the linear transformation for the neighbors. This is linear transformation for the node itself. Then we plus it. Then maybe we have some vector of appropriate sizes called bias, if you wish. So we do some linear combination of this thing and then apply some nonlinearity, sigmoid in this case. All right? Of course, this is, okay, so this is basically the model I will look at today, but we can have like many other variants of this. So instead of sum, we can have maybe average or max or something else. Instead of this linear combination of, we can have like some concatenation maybe somewhere here, and instead of sigmoid, we can have ReLU, whatever we want. And this different architectures may have their own names, maybe graph GCNs, this stands for graph convolutional networks, which I don't like this name, but very popular, or graph sage, or many other things. Yeah, just to make it clear, what is a GNN? People mean different things, but this is the same as usual neural networks. So basically, a GNN sometimes is just one particular instance with all the matrices trained, or sometimes a GNN is kind of GNN architecture. It's more like, okay, for this architecture with whatever A, whatever C, whatever B is, right? So I will maybe sometimes abuse this terminology and say GNN is either one particular instance or maybe the whole family without trained matrices. Anyway, so as we will see in a minute, oh, actually, yeah, even here, these GNNs realize node embeddings, functions on nodes in graphs. But it's easy to see that not every function is possible to realize, and even realize whatever it means, even approximate. But just as a basic observation without formalizing is that, for example, reachability, like classic reachability problem, is not expressible with these GNNs. So we can't find any this AC GNN which realize that the function, a node is reachable from a node with label 1, right? Why? Well, because each GNN has fixed number of layers, only like 5. And reachability needs to look arbitrarily far. For different graphs, it may be arbitrarily far, this node of, in this case, like, no, if it is 5 layers, okay, it's just 5, but this distance for reachability may be arbitrary. Another example is that, okay, these GNNs look only at the connected components of the node. They can't look globally in the whole graph. So for example, if we want to learn node embedding, there is a red node somewhere in the graph that is neither myself nor my neighbor. Arbitrary, like anywhere in the graph. We're again stuck, and not stuck only because it's reachability, we can't check reachability, but because we can't look at another connected component of the graph, right? And yeah, okay, so basically, for the first example, there are generalizations of this general architecture I presented in the beginning which can do it, like recurrent GNNs. Same here, GNNs with global readout can look in another connected components. Or, well, another example is that actually GNNs can't recognize cycles. They can't check whether a node is on a cycle of length 5. If you think about it, just, okay, we have this aggregation from the neighbors, and then for several layers. And everything GNNs can do is to look at the tree unravelings of the nodes, not anything about cycles, right? And this is actually a key idea of what GNNs can do or cannot do. But there are generalizations which can check for cycles. In any case, so we can see that GNNs can do something and cannot do something. We see many examples that they cannot do. And yeah, by the way, like any kind of approximation would not work on these examples, right? Okay, maybe it depends on what they mean by approximation, but still we can't say that we will find some approximation of reachability. This, for any reasonable notion of approximation, this wouldn't work, even like if we relax it. But anyway, so if we want to say GNNs can do something and cannot do something, but what does it mean? And apparently, there are different notions of this expressibility of GNNs, which pops up in the literature, and they actually usually called expressivity, but they mean different things. And this is a bit of unfortunate, actually, I would say, for the field, that people use the same word for many things. And actually, for people who are kind of advanced here, this is maybe my main message. Okay, some expressivities are different from other expressivities. Okay, for like advanced logicians here, well, in logic it's kind of the same. We have different notions of uniform, non-uniform expressivity and stuff. But anyway, in the world of GNNs, the first notion of expressivity which was used, and the most famous, I actually don't like to call it expressivity. I call it distinguishability or separability. We will see what it is. But this is what is connected to WL test and all these famous results, right? But this is what I don't like to call expressivity, because I find it a confusing name. For me, expressivity is, well, some people call it strong uniform expressivity. This is really what GNNs can express in terms of functions, as functions. And this is okay. I hope to have it as a main topic of today's talk. We'll see. There are a few more, like non-uniform expressivity, and this is somehow in between. We will maybe mention it in the end. Also, we can go to approximation, and some people say, oh, actually, approximation is also something which we can call expressivity. But even all of this is actually nothing about real learning stuff. And just, I maybe say it now. So, yeah, okay, all this, but this is the same as about, like, say, this universal approximation theorem. Yeah, you can approximate your function. You can approximate maybe all functions. That's good. You can express all functions of this type. That's good. But actually, can you really learn it? Can you really train for this? And this is like a completely different question. And for GNN, I don't know much about like normal neural networks, how good it is. But for GNNs, this gap between what I can learn and what I can express is huge. It's really huge. Most of the functions which you... So basically, okay, GNNs can look far if they have a good enough number of layers. But I don't know any GNN which can learn farther than 10. This is just impossible. And why is it? I actually don't know. And maybe this is what I want to discuss at the panel today. Anyway, so still like this expressivity, they are important simply because we can say something about the upper bounds. If you can't express something, if you think that you need to do reachability in your task, then sorry, like it's like don't use GNNs because they can't do this, right? And for all other types of expressivity, and like for checking cycles, for whatever. But it's important to say, if one thing is weaker in expressivity, what kind of expressivity doesn't matter, than another, it doesn't mean that it's worse. So universal thing is good, but if you have like you can look at this weaker expressivity as some kind of prior knowledge. So if you know that your function to learn in the graph needs to look at most distance 2, don't give your GNN 25 layers. These 25 layers will just add more noise, right? Of course, 2 layers is less expressive than 25 layers in terms of GNNs. Like, because they can look only at 2 steps in graph. But that's good sometimes. Sometimes it's just like the knowledge you have, that you just only need to look at distance 2, right? And same applies for any kind of this weaker expressivity. Nonetheless, I need to check how, I'm probably very slow. Okay, not that bad. Okay, thank you. Yeah, I should put it here. Nonetheless, so let's briefly discuss this distinguishability power. So actually, how many people here know about this Weisfeiler-Leman stuff? Who have? Okay, not that many. Some. Sorry? Yeah, okay, heard of. That's good. But so these are, in GNNs, these are first notion of expressivity connection to Weisfeiler-Leman test, and it became quite famous at some point, and still it's the most popular notion of expressivity. But let's brief, since I wanted to talk about this uniform stuff, so I will try to do it quick. So basically, we can define it, distinguishing power of a formalism, or at least compare two classes of node embeddings, or two formalisms which realize node embeddings. Think about GNNs or something else, it doesn't matter. Some classes of node embeddings in terms of their distinguishing power. And what does it mean to some class to be more expressive in this distinguishing power than in other class? It basically says that if we have, for the first formalism, if we have two nodes and two graphs which we can distinguish, we can give different numbers with some element, some node embedding in this class, maybe some particular GNN. Then in another class, we should have, like, also, we should be able to distinguish these two nodes. Is it clear, or should I repeat? Okay, so let me repeat, maybe reading this definition again. So a class of node embeddings, or equivalently, well, equivalently in the same way, maybe some formalism, maybe some class of GNNs, has as strong expressive distinguishing power as another class if for every two nodes in two graphs, like V and V prime and G prime, if there exists like some Xi member of C1 which can give different answers, then in the second formalism we also have some GNN which gives different answers for these two nodes in these two graphs. If we can distinguish with some GNN two nodes, then we should be able to distinguish them in another. All right? Good. And basically, this famous theorem, which is one of these examples when the theorem was proven in parallel by two groups of people, and they claim it's completely independent in the same year, is that these AC GNNs I presented to you have the same distinguishing power as, well, stable coloring off, doesn't matter, of the Weisfeiler-Leman test, right? Which is actually, I really like this result, and I like this type of results when we really take something from one field, graph neural networks, and something from like completely apart, like the first glance unrelated subfield of computer science. In this case, it's like Weisfeiler-Leman test is a test for graph isomorphism. Well, sound but not complete, doesn't matter. So graph isomorphism, like graph theory, graph isomorphism field, and neural networks, what are they do they have in common? When you like try to understand this theorem, it's actually fairly straightforward. But just to see this connection, this is, I think, quite nice all the time. Because, I really believe that there are ideas beyond formalisms. And here we see an example when the same idea applies, appeared in different things, and finding these correspondences is always nice. Anyway, so briefly, what is this Weisfeiler-Leman test? As I say, it is a test to check whether two graphs are isomorphic. We know that graph isomorphism is one of these strange computer science problems no one knows the complexity of. So no one can prove NP completeness. No one can find a polynomial time algorithm. So it is one of these NP intermediate problems. But in practical sense, we don't have a good algorithm for graph isomorphism. That's why Weisfeiler-Leman test is a sound, but complete but not sound test. So it may say that if it says no, then the graphs are not isomorphic. If it says yes, this yes should be interpreted as maybe. Maybe yes, maybe no. How does it work? Okay, so it inputs, of course, two graphs, well, originally with colored nodes, but for our case, it may be with node embeddings. So node embeddings, the vectors may be seen as colors. Most likely in our graph, all the embeddings, original embeddings will be different. That's fine. All the nodes have different colors. But maybe sometimes they have the same. And then we iterate until kind of stabilization, the following procedure. So we assign new colors to each node based on the following. We just look at the colors of the neighbors and the color of the node itself and check, okay, if these two informations is the same, for two nodes, we assign them the same color. If they're different, we assign them different colors. Okay? And then we repeat this until the classes of nodes with the same color stay stable. Of course, this may go for unbounded number of steps. So for bigger graphs, it may be more steps than for smaller graphs, the same procedure. And okay, we accept if at the end this stable stuff have the same multi-set of colors globally for all the nodes in the graph, and reject if we have different. So just as a simple example, we have like two graphs. In this case, all of them have the same nodes, same color for all the nodes, black. And then on the first step, we see, okay, this node it is black and has 3 black neighbors. Let's call this red. We put red here as the label for this node on the second, kind of after the first iteration. This node has 4 neighbors, all of them are black, and the node itself is black as well. Let's call it green. This node, okay, 2 neighbors and black itself. Let's keep it black. But the fact that this is black here and black there doesn't mean anything. So what is meaningful is only for the layer itself, like for the iteration. But anyway, so these 2 nodes are kind of in the same category. They have 3 neighbors, all of them are black, and they are black themselves. Call it red. And here, these 2 nodes also the same. And this is 4 neighbors, and so on and so on. Okay? So this is first step. Then we continue based on these colors. Continue until we stabilize. It's like easy to see that it will stabilize eventually simply because the worst case, all of the nodes will be different colors. But anyway, so here we see that the resulting, the stable coloring is different from these 2 graphs. We reject. And this is correct because if we say no, it is no. Not isomorphic. But this test, it's very simple. It's polynomial time, even simpler. This is why it's actually, well, not sound. So we may say, we may accept 2 graphs, so-called like, well, difficult for Weisfeiler-Leman, which actually say, here we actually already have stable coloring. And this is why, like, we can apply as many times as we want. We still have the same coloring, same colors for the graphs. We accept, but they are obviously not isomorphic. Okay? Right. And you may have already noticed some commonalities between these 2 things, right? So Weisfeiler-Leman, okay, what does it do? It aggregates the information from the neighbors of the node and combine it with the information of the node itself, like with the color of the node itself. So basically, it applies some injective function for the aggregation of the neighbors and the node itself, starting with initial embedding. GNNs do the same thing, in a sense, except that, okay, here it may be more complex aggregation function and, well, some combination function. And already looking at this, it's kind of easy to see that we can distinguish the same things with GNNs, AC GNNs, and Weisfeiler-Leman. Right? Well, the proof is straightforward in a sense, just looking here. Is it like more or less obvious for everyone? Okay, good. But, so why don't I like this to have, to call this power expressivity? Well, yeah, first of all, you will notice, okay, WL just on the very superficial level. WL test realizes a node embedding. Right? It assigns a color to each node, so it just realizes a node embedding. Each AC GNN realizes a node embedding, right? And AC GNN has the same distinguishing or expressive power of WL. And this kind of means, well, someone may think that it means that for each, that we can actually implement WL with AC GNN, in the sense that we can just find the AC GNN which does the same as WL for all the graphs, all the nodes on all the graphs, right? Okay, if it is the same expressive power, we should simulate WL with AC GNNs. But obviously we can't, because each AC GNN has fixed number of layers. But WL may run for arbitrary number of steps depending on the graph. So we can't actually realize WL with AC GNNs. And so you may ask, why do we have distinguishability, the same distinguishability power? But this is, the caveat is like non-uniformity. We need to be able to distinguish the same pairs in graphs, same pairs of nodes and graphs, but we can find a separate AC GNN for each particular instance. So, okay, WL distinguishes these two nodes in these two graphs. And we can find AC GNN which also distinguishes these two nodes in these two graphs. We just need to find good enough number of layers. This good enough number of layers will be, okay, safely the number of nodes in the graph. If our number of layers in the AC GNN has like more layers than the number of nodes in these two graphs, then we will be able to simulate WL for these particular nodes in these particular graphs, right? But if we want to simulate them uniformly, if we want to simulate WL for all the graphs, then we are screwed up, because WL test may stop in the number of steps dependent on the size of the graph, while each AC GNN has a fixed number of layers. Is this message more or less clear? Okay, I hope it is, because this is kind of the key intuition for the good notion of expressive power. So the good notion of expressive power is actually, which I called like strong or uniform expressive power, is that we really try to, for two classes of node embeddings, we want to simulate, we want just to find for each function we can realize with GNNs, we want to find a function which we can realize in another formalism. Maybe two GNN classes, or maybe GNN and some logical formalism. We want to simulate each function individually, each function in like for all the graphs, right? So if, for example, we have a CGNN and we want to simulate it with some bisimulation invariant function, then we really want to find a bisimulation invariant function which does exactly the same as ACGNN for all the graphs, right? And this is much stronger notion. Okay, so what's the time? Okay, fine. So here, basically, historically, the first result is actually, yeah, probably from me, is the connection to logic. Really, we can simulate, we'll see this result. It's a little bit more complicated than just simulating all ACGNNs with some logical formalism, but still relevant. However, I actually think that a nicer, or at least easier to understand result in this sense is connected to bisimulation. So who knows what is bisimulation? Okay, more than WL, which is kind of expected because bisimulation is much more known notion in computer science, which many fields invented by themselves. So I even tried to find who actually invented, is it any single person who invented bisimulation, and there is no such person because it was invented in many fields independently. So let's have a look at this bisimulation stuff. So just for those who don't know what is bisimulation, and actually we need a special kind of bisimulation anyway, so it's good to build up. So a bisimulation is a binary relation on nodes in graphs, right? So we just say that two nodes are bisimilar if they have the same labelings by themselves, and we can actually find bisimilar nodes in their neighbors, in a sense. So basically, okay, same labels by themselves, these two nodes, V1 and V2. And also for each neighbor of V1, we should be able to find a neighbor of V2 such that these neighbors are bisimilar. Okay? By the way, here, and also other way around. So two nodes should be the same by themselves, and for each neighbor of one, we should find a neighbor of another which are the same. Well, same, equivalent in a sense. Do this, like behave the same, like simulate each other. Okay? Of course, this thing is kind of, if you want to compute it, it's kind of, again, a stable fixed point in a sense. We need to saturate our bisimulation in a sense. So it may be that we need many steps to find this, but it's always possible. Well, formally speaking, there are many bisimulations. So for each graph, or for each two graphs, we can say that nothing is bisimilar to anything. It's also a bisimulation, but it's a trivial one. But it's easy to see that the union of two bisimulations is a bisimulation itself, which means that we can talk about maximal bisimulation. Right? So we can say that we can't find anything bigger at the end. And this is like the single one, which is bisimulation. Okay, but we don't need this notion of bisimulation itself. We need a variant of this. And the first variant, well, the first step is counting bisimulation. So here we are the same, except that now we respect the number of bisimilar neighbors. So in the first case, we may, like it's just for each neighbor of V1, we should find a neighbor of V2, which are bisimilar, these neighbors. Here we care about the numbers. So if like we have two neighbors, maybe even bisimilar between themselves, but it doesn't matter, then it should be two on the other side as well. If we have three here, we should have three there. Okay? This is counting bisimulation. It's a stronger notion, actually. So each counting bisimulation is a bisimulation, but not other way around, of course. Good. But actually what we really need, we need partial counting bisimulations. And here, as you may notice with this bisimulation, counting bisimulation, we may look arbitrary far in a sense. So we really need to find some kind of fixed point. While partial counting bisimulation, and where they are parameterized by some number, we just look at the depth L in this bisimulation. So zero partial counting bisimulation is just that the nodes have the same labels. No, I don't care about my neighbors. Okay? Then one partial counting bisimulation says, okay, I have this, like two nodes have the same labels, but also we have the same number of counting equivalent guys in the neighbors, but now with zero, right? So we look at depth 1. For depth 2, we have same number of partial counting bisimilar neighbors with depth 1, and so on, right? How many people I have with me now with this counting, partial counting bisimulation? Okay, some. But so basically, bisimulation, I hope everyone understood. Counting partial, we respect the number of neighbors. Partial counting with the number L, that we actually have a bound of how far we look. With counting bisimulation, we can look at arbitrary far. We need our neighbors to be bisimilar in the same way as the nodes themselves. While with partial, every neighbor step goes -1, right? So we start with 0, then we go, well, okay, if we want 5 partial counting bisimulation, then our neighbors should be 4 partial counting bisimulation, whose neighbors should be 3 partial count, and so on, until we reach 0, which just says the same label. And actually, yeah, so example of maximal counting bisimulation is the same coloring relation of the result of Weisfeiler-Leman. Right? So we have Weisfeiler-Leman. It assigns colors. And if we have same coloring, it is an equivalence relation, and it's maximal counting by simulation, in fact. While for partial one, the same coloring relation as the intermediate result after L rounds of Weisfeiler-Leman is precisely this thing. So actually, this bisimulation is, if you think about it, is a little bit of a rephrasing of Weisfeiler-Leman, but in a more uniform way, actually. Nonetheless, so the result, which is actually like more like a proposition. Sorry, before going to the result. So now, looking at node embeddings, we can say that it is node embedding, meaning functions or nodes in graphs. We can say that this node embedding is bisimulation invariant. And this simply says that it can't can't separate bisimilar nodes. So if two nodes are bisimilar, then we give the same, then the function must give the same answer. Okay? Bisimulation invariance. And then we can, of course, modify this definition for counting bisimulation or partial bisimulation in the same way. So we can't distinguish this, we can't distinguish that. And the result is, which is, as I say, it's more like a proposition, is that these AC GNNs are exactly like equivalent in this strong expressive power to the class of all partial counting bisimulation invariant embeddings. So actually, all the functions we can realize with AC GNNs are precisely the functions which are partial counting bisimulation invariant. Okay, you may think, okay, partial counting bisimulation invariant, this sounds a little strange because I don't have any number here, like 5 or 3. So maybe I can just drop this partial here and say counting bisimulation invariant, but no, it's kind of the same pitfall as we had with Weisfeiler-Leman. So actually, each AC GNN has a number of layers, maybe 5. And actually, AC GNNs with 5 layers are 5 partial counting bisimulation invariant, precisely. Each AC GNNs with, each partial, let's say, 25 partial counting bisimulation invariant function can be realized by AC GNN with 25 layers, right? So basically, this says that these AC GNNs and partial counting bisimulation invariant functions is precisely the same thing. Which again, this type of result, as I say, I like. 2 minutes. Oh, okay, not much. Is it just really 2 minutes? Oh. Okay, give me a little bit more. Okay? Right. Yeah, okay. So fine. So, as I say, these two things are the same. But it's good to remember that we are in the settings of AC GNNs. So, for example, like AC GNNs are not constructive in a sense that maybe, so there are partial counting or even bisimulation invariant functions which are not computable. No problem, there are such functions. And you may say, okay, how can I realize it with AC GNNs? But no problem, I can find aggregation and combination functions which are not computable. Same thing. Of course, real GNNs are all computable. We have these matrices and stuff. But this is because my model AC GNNs is actually not, in general, they are not always neural or whatever, because they, like I just say, arbitrary aggregate, arbitrary combine. Right? But this is a good upper bound. Nonetheless, so I should probably overview very quickly what else is in this field. And basically, connection to logic, which is probably the first result in the field of like this uniform expressive power, is that okay, I hope more or less everyone understands that these graphs I presented have something in common with logical structures, right? Okay, I have one type of edges, I have undirected edges, Yeah, sure, but this is the common grounds is fairly straightforward. And also I have output, yes, say yes, no output, same as in logic. Plus, okay, another thing is that in logic we usually have unary predicates ABC for each node in the graph. GNNs have vector embeddings, right? So they assign to each node a vector of numbers. But we can always represent ABC as like basically position encoding, like assigned to each unary predicate a position in our vector and represent our nodes, our logical structure as a graph with node embeddings, with numeric node embeddings like 0, 1, categorical embedding. And then, having like these common grounds between logic and GNNs, we can start to study this expressivity of logical formalisms, the connection of logical formalisms to GNNs, right? And actually the result, which is kind of famous, is that, but okay, of course it could be good to find some logic which captures all AC GNNs, at least for these like logical structures. Could be nice, and there are such results, but as you can imagine, this logic will be absolutely crazy, in the sense that like AC GNNs, well, okay, all AC GNNs may be not even possible, but some very large class of AC GNNs. But these AC GNNs, even like neural version of, they do like matrices, they have non-linearities. Expressing this in pure logic may be a bit of problematic thing, obviously. So basic, but still it could be good to find some common grounds, and this common grounds is this theorem, which basically says that a node classifier, this like function which assigns yes and no to each node in each graph, is realizable by both AC GNN and first order logic. So I basically intersect AC GNNs with first order logic, and then I get precisely graded modal logic. And here it's a bit kind of interesting that I get precisely, I intersect AC GNNs with something very different, first order logic. Well, unary formulas of first order logic. And this intersection is precisely graded modal logic. If you don't know what is graded modal logic, it doesn't matter, but it's famous formalism in logic, some fragment of first order logic. Okay? And well, one direction here is fairly straightforward. So the fact that, okay, that you can write graded modal logic formula as an AC GNN is a technicality, it's not a problem. But the other direction, so just using the fact like that we are AC GNN which is expressible somehow in first order logic, and suddenly like we can express this AC GNN in graded modal logic, this is kind of not obvious at all. And here I should say that we were really lucky that when we found it, like came to this question, we immediately found a very recent paper which basically does the job for us. And this, what do we need? If you are familiar with Van Bentham theorem, which basically says that bisimulation invariant fragment of first order logic is precisely graded modal logic, which is like a famous theorem, really. And we already have this connection of AC GNNs to bisimulation. And well, this theorem is a generalization of Van Bentham theorem to, oh, sorry, well, I said wrong about Van Bentham theorem. Van Bentham theorem says that the just normal bisimulation invariant fragment of first order logic is just modal logic. This extension, which was actually recent, generalized it to graded modal logic. So it says counting bisimulation invariant fragment of first order logic is precisely graded modal logic. Okay? And basically using this theorem, we could prove the other direction of this theorem, which is about AC GNNs. So here, I also like this result. By itself, it's okay, not very deep, but because it relies on deep stuff which just recently existed. By the way, if we want to maybe, I will say some concluding stuff, but just interesting fact. You can it's not very difficult to write this theorem for graph level. So here I always concentrated on node level classifiers. I say functions like AC GNNs, which says me yes and no for each node in each graph. And then I have this. Formulating it for graph classifiers, which basically says yes, no for each graph instead of node in each graph, it's no problem. You can formulate this. Okay, it's not a graded model, but something similar. It's not like, but yeah, so first order logic, no problem. First order logic sentences. We can formulate this theorem, but we can't prove this theorem. One direction is easy, but we don't have this one Bentham style for graph level. And actually there are people who are thinking about it and they just can't prove this theorem for graph level. So you think, okay, what is the difference between node level and graph level? Should be the same. But here we don't have this, the same thing. I still believe the same theorem holds for graph level, but how to prove it? Okay, we don't have this thing. Nonetheless, so I probably, as the bosses say I should stop somewhere here. I just very briefly mention what else happens here. So for logic, could be nice to restrict our class of GNNs, for which we will have like a corresponding exact class of logic, like logical formulas, right? So maybe we don't take all AC GNNs, but take something subclass of AC GNNs, maybe also trainable, of course, for some matrices and nonlinearities, so proper neural networks, for which we have a logic, really, exactly in terms of expressivity. And this is possible for different notions of for GNNs we have these type of things. For very simple, we have very simple class. For example, unions of tree-shaped CQs have exactly same expressive power as actually quite a large class of GNNs, so-called monotonic max GNNs. And more expressive GNNs have more expressive logics corresponding. Sometimes we actually have only one direction. We have logic more expressive than GNNs. It's also interesting, right? So having GNNs more expressive than logic is like less interesting. But logic more expressive than GNNs, this is kind of nice that we can capture neural architecture with logic, right? Sometimes we do have existing logics which capture some class of GNNs, but sometimes we have like by-purpose logic which captures some class of GNNs, which is a bit, well, but still interesting. Right, and well, just to last thing is that, of course, we can find some other notions of expressivity. This uniform expressivity is actually very strong, but we maybe sometimes want to relax it somehow. There exists this non-uniform expressive power which lies in between distinguishability and uniform expressibility. I don't stop here. But also you can think about approximations, of course. Since we're in a neural world, doing like exact capturing in terms of expressibility is a bit like of a stretch. In theory it's nice, but in practice, who cares, right? In neural world we want to approximate stuff. Good notion of approximation on graphs is actually still to come, I would say. Because there are these notions of approximation, but they just do approximation of the level of the numbers of embeddings. But I want, in the world of the graphs, I want a notion even of approximation which may be, so in most, what I want, on most of the nodes of the graphs, I give very close answer. But sometimes I can make mistakes, even on the level of graphs. So for some nodes, I may have huge mistakes. I don't care if it is like a small fraction of. And this is actually yet to be defined because the current notions of approximations are just telling, okay, it should give very close answer in terms of numbers for all nodes in all graphs. So I find it too strong. Anyway, so just as a last thing, as a wrap-up, it's a fascinating topic, but it's actually really hard to get results. And people working, people thinking, but not very quickly. So I think all the easy things are there. The recent papers, if they come, they are complicated. But it's also nice to work on, and I think it's a nice connection between neural networks and logic. So for logicians, it's a good opportunity, okay, at least for young logicians, to sell themselves, saying, okay, I'm doing neural networks, because this type of works are actually very welcome in machine learning conferences. And then, well, did I do this? To some extent. So just to sell myself, I don't say that my work on these GNNs is the most exciting I ever done in my life, but it's definitely the most cited. Right? So in terms of promotion, it's a good thing. You know, logicians suffer from this, right? No one cares. Here someone seems to care at least. All right, so thank you. I don't know how I am with time, but some time for questions.
Thank you, Egor. Great talk, and we have some time for questions. Anyone who would like to ask a question?
Thank you, Egor, for your talk. It was very interesting. So have you looked at the connection between the expressibility and sample complexity? Is there a connection for class of functions that have less expressive power to be learned faster, right? With less data?
Yeah, I understand your question, but I don't know about any work in this setting for graph neural networks. So basically, yeah, in a sense, this graph neural network, at least theory community, is probably kind of behind the expressivity of other, like of these similar fields in other neural networks, right? So RNNs, you are doing this, like just even normal neural networks, like all this binarized stuff. It's a lot of space for like reusing the, you say sample complexity, but whatever, trainability, all these things. We are definitely behind because we have actually the questions which I kind of discussed today and many other questions in this field, they are just not interesting in for normal neural networks. Here we have to actually, we have two dimensions. We have numbers, vectors of numbers, but also complicated graph structure. While for, like, say, neural networks, we don't have any complicated graph structures, and we just work with vectors. For RNNs, for example, we work with strings, which are presumably easier than, okay, unary, okay, linear graphs. No, okay, but at least, okay, easier, of course, not like always, but still, I guess you can imagine that graphs are more complex, at least at the first look. Okay, fair enough. So no, I don't know, but if you wish, you can explain me, well, we can, I don't know, discuss if you wish.
We can discuss it during the panel.
Exactly, yeah. That's what I wanted to say, that later today we're going to have a panel. The topic is expressivity of neural networks. Egor is one of the participants. Another one is myself. And these all sound like interesting questions, and I think we can have a fight on whether, you know, studying expressive recurrent neural networks is easier than studying expressivity of graph neural networks. Are there any more questions?
Thank you for the talk. Very easy to follow. Oh, so if I understand correctly, these ACGNNs cannot distinguish between two graphs which are two cycles of different length. Is that true?
Yeah, I would think so. Yeah,
Yeah,
absolutely.
Like, can we like increase the expressivity of the model by considering the dual graph of the input graph, or I don't know, considering like a graph over pairs of vertices?
I have a slide for this. Okay, slide, half of slide. So yeah, we can. Yeah, we can. Basically, you know, like tree width, I suppose, right? So we can generalize our GNNs so that instead of nodes, they will work with pairs of nodes, and then with these pairs of nodes, we suddenly will be able to recognize tree width too.
Nice, nice.
So yeah, this type of work exists. The problem is that in practice, for any reasonable size of graphs, you have quadratic blow-up. So they are not really that much used in practice simply because you don't want to do the Cartesian product of the graph to itself, basically. There are some intermediate things, so you can basically, well, in the most simple case, you may say, okay, I don't do like a new node for each pair of nodes, but I do each new node for each pair of connected nodes, for example. Then it's not a quadratic block, then it's small, because like the number of edges is presumably quite small, right? But then, there is actually quite a lot, especially in this distinguishability power, there is a huge pile of literature to find this like fine-grained border between what we can do in practice and in terms of like what we can distinguish. And you spotted a very interesting question.
Yeah, thanks. A very interesting connection to tree width. Thank you.
Okay.
Thank you for the talk. When you were talked about how it was similar to WL, it seemed to me that the aggregation function was doing a lot of work in that similarity, because it seems to me like a simple summation aggregation function wouldn't be the same expressivity. And I was wondering, first of all, is my interpretation correct there? And then does that apply to some of the other cases? Like, do you need a complicated aggregation function in order to have the same expressivity, or is it a simple one like
well, okay. So I'm not 100% sure if I understand your question, but what I can say is that there is aggregation function is very important. So if we come back here, and this is a subtle question here, actually. So yeah, so here, what do we want? To simulate this Weisfeiler-Leman with AC GNN. Here we have injective stuff, right? Injective means that we should give different answers for all possible multisets. And of this plus that, but this is okay, this is not important. For all possible multisets, different answers. And if our aggregation is summation, then sorry, it doesn't fit, right? It's not injective. And does it exist? Actually, even can we find any reasonable function based on some, okay, of course, we can find an injective aggregation function. Like, you know, like, okay, your favorite 0-1, like binary encoding of multisets, of vectors, will work. But of course, it's not possible to implement it. So can we actually do it? And this is a good question. And actually, the answer is no, we can't. There exists no, well, here I don't want to go to the details, but there is no reasonable aggregation function with some good properties which is injective. For WL, it is actually not a problem. For this result, for distinguishability power result, it is not a problem. And it is not a problem because we care about distinguishability. And for distinguishability, we can restrict to the graphs of this particular size. We need to find the GNN for each particular pair of nodes in particular pair of graphs. And these graphs have particular size. And if we restrict for this size of graphs, then we can find a reasonable function which is injective for this particular size of the graphs. But when we want all graphs for uniform, for example, case, this suddenly doesn't work. And this causes actually quite a lot of problems. Does it answer your question?
Yeah, I answered the first half, and so I think my understanding is similar to what you just said. And my question is, the other results that you presented later, do they have similar complex aggregation functions, or can they be done simply?
Well, for uniform expressive power, for uniform expressivity, we do need, if we want to express like reasonable stuff, we do need, so for example, if we want to find a GNN, AC GNN, which simulates WL for all the graphs. Okay, one problem is that we can't look far away. But another problem is that we need injective function, which injective all the time. And such a function doesn't exist in a reasonable way. So arbitrary aggregation function, yes, exists, but for a reasonable one, whatever it means, trainable one, doesn't exist. And there is a theorem for this, doesn't exist. So yeah, it is a big problem. Well, big. kind of big problem. It makes it interesting to study in theory what we can actually express in this uniform setting if we can't even express WL, even if we do like the recursive version, which can look far away, arbitrarily far away.
So we need to move on to the break now. Let's thank Egor again.